Okay, so thank you for the introduction. I'm Marcin Kulka. I'm from Warsaw. I'm software engineer in 9lives Data Company, and I would like to talk about our technology that fully automates predictive analysis on Apache Spark. I prepared this talk together with Michał Kaczmarczyk, but he's absent today here. And two words about our company, 9lives Data. We are an advanced software R&D company based in Warsaw, with over 75 scientists and software engineers, and we specialize in scalable storage, big data, and distributed systems, and we cooperate with partners from US, Japan, and Germany. And this technology I'm going to present is actually the result of cooperation between 9lives Data and NEC. And this technology itself was also previously presented at 2 Spark Summits by Masato Asahara and Ryohei Fujimaki, and by Michał Kaczmarczyk and me. Okay, so let me first share the agenda of today's talk. So this talk actually will not be about huge data. Instead, I'm going to talk about many predictive modeling processes. I will start from presenting typical use case for predictive modeling problem, and it will turn out to be a work-intensive and time-consuming problem. So we will see the need of automation, and it will lead us to our technology, automatic predictive modeling. Then I will show you design challenges that we faced, and finally I will share with you evaluation results. Okay, so let's start from the motivation. So as all of you know, the whole artificial intelligence and also predictive analysis becomes part of many enterprise applications. And that's why it influences the whole industry and business world. But predictive modeling itself is actually difficult. It takes long time, possibly weeks, and it requires high skills, possibly PhD class skills. Let's now look at the typical predictive modeling use case. So we start from the data, training, validation, and test data, and we would like to achieve prediction result for our test data, and we would like them, of course, to be highly accurate prediction results. So we actually would like our data scientists to provide us models, predictive models, that will give us highly accurate prediction results. Okay, now let's look at the work of our data scientists. So it actually consists of a few steps. First is algorithm selection. Our data scientist must choose the proper model type. He can choose a very simple one like decision tree, linear regression, or he can move to something more complicated like, let's say, deep learning model, which possibly can give us higher accuracy. But at this point, we must remember that there is actually the balance between accuracy and transparency, and actually many real business use cases require that we understand why we provide that specific value. Okay, the next step is hyperparameters tuning. So data scientists must tune the parameters of the models he chose. And the last step is feature selection. So data scientists must determine a set of features that are highly correlated with value we would like to predict. And actually this whole process is a lot of effort. Many models could be produced during this process. It is taken actually in iterations, not sequentially, and it could possibly take weeks. And of course, it requires very high skills. So what we give is a full automation of this whole process, and at the end we provide highly accurate results, and the whole process takes a short time. Okay, so now let's dive deeply into our technology. So what we do, we explore many modeling possibilities, to start from data preprocessing strategies like missing value imputation policies, standardization policies, random sampling policies. Then we go through many possible model types like linear models, decision tree models, some more sophisticated model types, and also ensemble models of all of them. At this point, also machine learning algorithm that provide us feature selection is performed. And the last space that we actually consider is the space of hyperparameters. Hyperparameters like initial depth of a tree or some regularization parameters for a feature selection algorithm. And when we actually intersect all these spaces, we will get thousands of models, and it would be very difficult to compute all of them on a single server. It possibly could take weeks. And so here's the place where Spark comes and helps us by distributing the whole computation across many machines and accelerating the whole process so that we can complete it in hours. And for those of you who actually don't know Spark, this is kind of a platform for fast in-memory computing with implicit data parallelism and built-in fault tolerance. And the base structure in Spark is RDD, which is abbreviation from Resilient Distributed Dataset, and it could be treated as a distributed collection. Okay, so let's come back to our technology. So now I will show you two flows of our application, modeling flow and prediction flow. Modeling flow, which consists actually of training and validation. And let's start from the modeling flow. So at the beginning, we have to have prepared data, training data, and basing on this data, we create training models, which then are validated using validation data and validation criteria provided by the user, so that we can we have these models validated. We have some validation prediction scores, and we can select best model or best models, which then can be taken to the next flow, prediction flow, together with some data, test data, and at the end we can provide some prediction results. And and of course the whole process is fully automated. Okay, so now let's move to the challenges that we face during our design and implementation, challenges and solutions for them. And these challenges are actually mostly related to the performance, execution performance. And let's start from the first one, using native machine learning engines in Spark. Okay, so first we should actually answer why we would like to use native machine learning engines in Spark, as they have actually completely different natures, native machine learning engines and Spark. And to answer this question, I would like to actually compare Spark and native machine learning engines. And by saying Spark, I mean actually Spark together with some distributed machine learning engine like Spark ML. So let's start from the scalability, first feature. So of course, we have scalability in case of Spark, while there is actually no or very limited scalability in case of native machine learning engines. Then choice of algorithms, which somehow possibly influence the final accuracy. And I would say the choice of algorithms is, there's some choice of algorithms for Spark, as not all of the algorithms are actually implemented. Not all of them could be implemented in this distributed way. And on the other hand, we have many implementations for native machine learning engines, possibly some historical implementations, some custom implementations, and they are all very efficient. And the first feature that I would like to compare is performance. And of course, we can compare performance only if data fits a single server because of this native machine learning engines. And performance is medium for Spark. Medium because of the some overhead on the synchronization and because of this distributed nature of it. And I would say it is high or extremely high in case of native machine learning engines, which are often very optimized. Okay, and here I would like to stress this last feature, performance. This is for us the most important, as we would like to compute thousands of models. We would like to be very fast. So when we look at this table, we see that actually we would like to have something from Spark and something from native machine learning engines. We would like scalability from this Spark and the others from the native machine learning engines. And that's actually answer on the question why we would like to combine these two, Spark and native machine learning engines. And now I would like to show you how we actually combined Spark and native machine learning engines in our application. And first for training flow. So we start from data, training data, which is in Parquet format on HDFS. Then we spread this data across many servers, and we perform some data preprocessing in MapReduce paradigm. This is the, let's say, the first phase. And then there's a second phase, machine learning phase, where we run simultaneously many machine learning engines in a Spark map operation. And for the simplicity of this talk, we may assume that a single machine learning engine is actually executed on a single Spark executor. And now we somehow must combine these two phases, the data preprocessing and this machine learning phase. So we have to actually satisfy the input requirements of this second phase, machine learning phase. Input requirements like the size of data that could be read by a single machine learning engine and the format of data. So here is how we do it. So first we downscale the data by random sampling. And then we convert the data in an initial format into the RDD of matrix, dense matrix. And then this data go from machine learning engines, and finally we write down the result, thousands of models on HDFS. And here I'd like to notice that in this intermediate phase we used RDD of huge and efficiently stored objects optimized for machine learning computations, this RDD of dense matrices. And so here actually Spark is used for parallelization, only for parallelization, and the advantage is that all the necessary data for a single execution is kept without memory overhead, any memory overhead. And what is more, performance critical operations are executed first on objects with linear algebra optimized, operations optimized, and also by fast and fast native machine learning algorithms. Okay, and now I would like to show you how we combine Spark and machine learning engines for the second flow, validation flow. We start similarly to the training flow by reading data in Parquet format from HDFS and spreading it across many servers. Then we perform data preprocessing. And then we don't do any downscaling. We just convert the data into the RDD of matrices. And then there's a prediction phase. So we would like to have prediction results for each model, for each data set actually. So the prediction results for a single model will be spread across many executors, across many servers. And then in the next validation phase we must rearrange those data so that prediction scores for a single model are located on a single executor to be able then to perform selection of the best model, and at the end the final results are written to HDFS, and we have this best model. Okay, and then third flow, prediction flow, and this is very similar to the previous one, validation flow, with the difference then in a prediction phase we don't have to compute prediction scores, prediction results for many models, but only for a single one, this previously selected. Okay, and now let's move to the second design challenge, parameter-aware scheduling. So as you remember, we actually consider many data sets in our applications. We also consider many parameter sets. Parameter set consists of data preprocessing strategy, some model type, and some hyperparameters. And actually what we schedule in the machine learning phase is not only the data, it's a pair of data and some parameters. And it's very important to schedule it efficiently. So now let's look at the let's say naive scheduling, which I would call is parameter centric, where we actually on a single executor consider single parameter set and many possible data sets. And we see that this is in this approach we actually waste a lot of memory. We have to load data from other servers frequently and also convert those data frequently. And of course, nobody will implement it in this way, but we may meet actually this situation when we have something like a random solution. And instead, we propose parameter-aware scheduling, where we, which I would say is rather data-centric, where we, on a single executor, have a single data set and many possible parameter sets. And in this approach we save the memory, we don't have to load data frequently from other servers, and we don't have to convert the data frequently. Okay, and now the design challenge number 3, predictive work balancing. So machine learning phase is actually the phase in our whole flow, in all our flows, that is actually the most work intensive and time consuming part. And we must ensure that the work in this phase is balanced and parallelized very well. So now again, let's look at the naive approach, naive balancing of models to be computed. Let's look at the server number 1, who actually got 2 complicated models to be computed, and it took it 10 minutes to finish. And the other server number 2 got very simple models to be computed, decision tree models, let's say, and it finished very quickly after 2 minutes and then idled for the majority of time. And so that was actually the waste of resources. So instead we propose predictive balancing, which actually could be done only if we actually somehow can estimate the work, estimate the work that is needed to compute some specific models. And in this approach, we can schedule complex models first. This is the first thing. And the second thing is that we can balance complex and simple models. Okay, and now let's move to the evaluation results. So we performed evaluation for a prediction problem comparing top 10 precision of targeting potential positive samples. And we compared our results with manual predictive modeling done with scikit-learn with some selected algorithms, logistic regression, SVM, random forests, and with some selected preprocessing strategies where almost all parameters of these algorithms were set to default values. We used competition data, KDD CAP 2014-15 and IGCAI 2015. And for our evaluation, we used NEC server, the X2000, with about 270 cores and 2 terabytes of RAM. And the results are very satisfactory, so the results of our technology are actually better than logistic regression and SVM and comparable with random forests. But what is very important for us is the short execution time of the whole process and the fact that the whole process is fully automated, so we didn't have to perform any data preprocessing, we didn't have to tune any parameters. And also the additional benefit is that we actually handle the data of almost any size. Okay, and now let me summarize this talk. So we started from the predictive modeling problem that actually is a difficult problem, requires sophisticated knowledge and takes a long time. And it actually led us to our technology, automatic predictive modeling, which combines Spark with native machine learning engines and fully automates the whole process. It also provides us highly accurate results and in quite a short time. And the additional advantage is that we can handle data of almost any size. Okay, so when it comes to possible future work, we plan to extend our model set of some other models like deep learning models, and we also think of speeding up by GPU, and that's all from me. Thank you.
Thank you very much, Marcin. Any questions? Oh, there's one at the back.
Hi, pretty impressive results. The question probably most of us may have, should now all data scientists just go home? I mean, do we need them? What for do we need them at all?
No, so actually this could this system could be used by data scientists instead of let's say standard tools. So it's it could be used and treated as a very helpful tool for data scientists to improve their work.
But I guess they wouldn't have many decisions to make, right? They just take the data, flow it through, and it comes out as a model, right? That was the question, I guess.
Okay, but remember that of course you have to prepare some features for the system. That is something that is actually not addressed by this system.
Hi, very nice presentation. I have a question regarding downscaling of the data. So the data is static under certain time and you downscale it and then every model receives the same copy of the data, or it's this done in a different way?
So we have the initial data, then we perform downscaling so that we have, let's say, 50 or 10, let's say tens of different downscaled data, and actually each because I was talking about data and parameters, yes? So then we intersect these possible data sets with parameter sets, and so actually we perform computation then. For each data, we perform computation for each possible parameter set. So yes, for every model, yes. So the specification of model is a part of parameters, yes. I treat it as a part of parameters.
Maybe one more question there.
Thanks. I have a question how you handle linear hyperparameters searching, because you end up with a very huge hyperspace, space of hyperparameters. So how do you handle that? Do you have any algorithms that actually work?
Well, how do we handle? Could you precise your question?
Because you run the models with different hyperparameters sets, and when you have a linear hyperparameter, then you might have an infinite amount of values. So you need a way to actually look for the best sets. And do you have any experience with that?
So we rather have some predefined, let's say, parameters. We actually don't explore the whole possible space of hyperparameters.
Yeah, sure. It's a big, like, infinite space. So
yeah,
in some approach.
Yeah, we concentrate of some predefined, few predefined.
But you don't use anything like Monte Carlo or bisection or.
No.
Okay. Thanks.
Okay, I guess these are all the questions. Excellent. So thank you very much again.
Thank you again.
And